these are memory cells. Now what we are talking about is memory arrays. So typically for these two terminal devices, we arrange them in the form of a crossbar array. So what exactly is a crossbar array? So in a crossbar array, you have these horizontal rows, which are known as word lines, and you have these vertical columns, which are known as bit lines. And you see at the intersection of all of, like, between each of these word lines and bit lines, you have a memory cell, right? So a memory device exists at the intersection of horizontal and vertical electrode. Now, why I call it as an intersection of horizontal and vertical electrode? So this is a way of representing where it's not very evident. Here you just note that, you know, you have a memory cell between each of these word lines and bit lines. When you look at the top view of how it is integrated, this is your bit line and this is your word line. And in between these two, this memory cell is there. So this is the top so this is the top electrode, there is the bottom electrode, and in between the top electrode and bottom electrode, the device stack will be. Now the best part about these devices is that their dimensions can be real small. So typically we represent the spacing between, you know, the interconnects of DRAM. So let me talk about this F first. So F is basically called the critical feature. What exactly defines F? F basically is defined by half pitch length. What is half pitch length? Half pitch length is the difference or distance between, you know, two adjacent interconnect lines in a DRAM. So DRAM interconnects are supposed to be the highest density interconnects. So the difference between the two, the distance between two interconnect lines in a DRAM chip is actually called critical feature size, F. Earlier, what used to happen that, you know, let's say when you talk about 40 nanometer technology or 180 nanometer technology and so on, it doesn't represent the gate length. It actually represents this F. 28 nanometer technology means distance between two DRAM interconnects is actually 28 nanometers, right? So that was a definition. However, this definition doesn't hold true beyond 14 nanometer technology node. So beyond 14 nanometer technology node, if you talk about, let's say, you know, this 5 nanometer technology node, 10 nanometer technology node, 7 nanometer technology node, it doesn't mean that these two metal lines, these two interconnect lines in the DRAM of that technology is separated by 14 nanometers or 10 nanometers or 7 nanometers. No, that's not true. Beyond 14 nanometer technology node, technology names are just names. 5 nanometer doesn't mean that any of the feature is 5 nanometer. It simply means that, you know, from 7 nanometer, we have reduced the technology node to 5 nanometer. So now it's just for namesake. In terms of dimension, nothing is reduced. So this is a concept which you should, you know, remember. Nowadays, reduction in the name, technology name, is just a reduction in the technology name, not the reduction in the critical size or not the reduction in any of the features of the chip. Earlier, this was true. Every 1.5 years, technology node used to go down by 0.7, factor of 0.7. Why factor of 0.7? It's 1 by root 2. Think about it once. And in the discussion session, if possible, let me know why exactly these go down by 0.7. So from 28 nanometer, they'll go down. Then from, let's say, you know, 14 nanometer, you multiply it with 0.7, it should go down to 10. 10, you multiply it with 0.7, it goes down to 7 nanometer. And, you know, there are also other technologies. So in between 10 and 14, there's also a 12 nanometer node, which is called half pitch node. So these are just names. So when industries were not getting sufficient, you know, advancements or sufficient benefits from 10 nanometer, they actually moved only half pitch from 14 to 12. TSMC did that. So nowadays it's just a name. Now from 5 they'll go to 3, from 3 they'll go to 2 point something and so on. But inherently the critical feature size or the size on the chip, that doesn't go to 5 nanometer or 3 nanometer or 10 nanometer. So basically, even when they are names, I mean, the critical feature size is close to 14 nanometers even there. So what exactly makes these two terminal memories very promising is that they can be accommodated having an area of 2f square, like 4f square itself. How 4f square? So you see, if you measure from, you know, this middle of this electrode to middle of this electrode, the distance would be f plus f, that is 2f. So from here to here, like from this, like from middle of let me talk in this way. So from this gap, middle of the gap to the middle of this gap, that dimension will be also f plus f 2f. So in the horizontal direction as well as in the vertical direction, the dimension is 2f for this memory cell, and hence the area that it occupies on the chip is only 4f square. If you take the case of a 3-terminal device such as MOSFET, it requires an area of at least 6f square, right? So with these 2-terminal memory devices, resistive RAMs or resistance change based memory devices, best part is that their density or their size is pretty small, so their density would be very large. Why density? Density is basically the number of cells that can be accommodated in a particular area. If area is limited already, right? In given area, if the size of the cells are small, then more number of cells can be accommodated, right? That is the fact. So since these devices, they take only 4f square of media, 2f dimension in the vertical, 2f in the horizontal, therefore the cell size is pretty small, and it can be made even, it can be further reduced. How it can be further reduced? How density can be further increased? Let us see that. So this is how these are arranged. So you have these bottom electrodes, you have these top electrodes arranged in a crossbar form. At intersection of each of these top electrodes and bottom electrodes, you have this stack and hence the memory device, right? Now the best part is here the effective cell area is 4f square, but you can stack several such cells in parallel. So the main thing that you have to consider while stacking is that if this is going from these metal layers which you are stacking on top of each other, they must be orthogonal to each other. So if this is going from here to here like this, the top electrode will go from this to this. And again, if you want to stack another layer on top of it, it will go again from this, like in this direction, like this. So you see here, you have this bottom electrode, then you have top electrode which is orthogonal to this. Then the top electrode of this cell is actually orthogonal to this, orthogonal to this previous layer. And similarly, the next cell, top electrode, is orthogonal to it. So you just by ensuring this orthogonality, in laying out these metal lines or top electrodes and bottom electrodes for the individual cells, you can actually realize a 3D integrated cross-point memory array where the effective cell size reduces by a factor of L, where L is the number of layers that you have. So in the same amount of area, earlier you were having one cell which was having an area of 4f square. Now in the same area, I mean area in terms of the top, like layout area, or the area while looking from top. Now in the same area, you will have 4f square divided by L cells. Like effective area would be 4f square by L, or the total number of cells would be L. So that is an advantage which you can exploit because of its 2-terminal nature, right? So 3D stacking can be used further to improve density, but that doesn't come up so in VLSI, nothing comes for free. Whenever you are introducing these things which are improving area, there would be something which would decrease in terms of performance or in terms of energy. Here also something happens. So in cross-point array, in any cross-point array comprising of 2-terminal devices, here I am representing those by these resistances. Let's say this is the device which I want to read. Since it's at the intersection of this row and this column, I put my amplifier or sensing circuitry to this column and apply my voltage to this row, so that the current actually goes through this and then I read it out. So to measure the resistance, effectively we can measure the current, and that gives you the resistance as well, right? If you know the voltage of it. So I apply a voltage to read the state of this device, and I want that this current should pass through this device and then come to this sense amplifier. However, since current depends on the resistance so current path depends on the resistance that it sees, right? If the situation is such that this resistance and this resistance are actually, sum of these 3 resistances is very small as compared to this cell that we are trying to read. So what may happen, the current, instead of going through this cell, may go through this. I mean, it will definitely go through these cells like this. Why? Because current always takes the least resistance path to flow, right? So if the situation is such that the neighboring cells are very low resistance as compared to the cells which we want to read or program, then it may so happen that the current actually passes through the other cells or through this sneak path. So this path is called sneak path because the current is not flowing through the main path, but it's taking a sneak path to flow. And this leads to something which is called current sneak path problem. So the selected cell, this current is not measured, its resistance state is not measured. Instead, what is measured is resistance of these three devices. So to avoid that, to mitigate this, what is done? We use basically a selector device in series with it. So along with this memory element, we apply a series access device or a selector device, which actually is like a transistor, which is actually like a switch. It's not a transistor, it is actually like a switch, which provides only unidirectional current flow. So these access devices, how they help in that? So if we have series of transistor, like if we have like series of this memory device as well as this access selector, or just think of it in this way. We have all these resistances now replaced by resistance and a switch in series. So just by controlling this switch, we can actually control through which cells the current flows. For instance, if we have such elements now between the electrodes, if we turn off the switch of this and this, if we somehow can turn off the switch, then we'll be sure that the current only flows through this, because only the switch of this is turned on and rest others are turned off. So by having this selector or a switch in series with this memory element, we can actually remove or mitigate this sneak path leakage current. So what can be those switches? There can be transistors, there can be ion-based switches such as MIEC. It can also be a tunnel-fed based, access selector. So there are several kinds of switches or these selectors that people have proposed. Most promising is your ion-based switches because they are also two-terminal. Okay, or ovonic threshold, ovonic switching-based selectors, which are also two-terminal based on like AGOX devices. Anyways, so with this discussion, let us summarize what is exactly we need from any memory, or what are the desirable characteristics out of any memory. So first is cost. Industries are always governed by the cost. So cost per bit should be as small as possible. Second, they should be low power and they should drain as less, battery power as possible. Then high speed of reading and writing, right? We want to access data very quick, and that is why it should be high speed. It should also be high endurance. So endurance is basically the number of cycles for which the device works perfectly. As I told that in flash memory, you have that tunnel oxide, you're forcing current through it. So after 10⁵ cycles of operation, that tunnel oxide degrades. Operation of the device is affected. It may even break down. Because of that, what happens? The device is not usable after 10⁵ cycles of programming. So endurance basically tells you after how many cycles of programming the device fails. And you need to have a very high endurance because you want your device to perform well for different applications. Again, density should be high. That is, its cell area should be as low as possible so that you can, accommodate as many memory devices as possible in a very limited area. And for that, 3D integration, 3D integration is one of the most promising ways. Another point is high retention. So retention is the ability to store data for a particular period of time. Larger the period, more beneficial it is for the memory. Industry standard is that your memory device, if it retains the data for more than 10 years, it qualifies for an industry grade memory. So retention should be high. Then it should also be secured. Why it should be secured? Because you should not be able to, any adversary or any, attacker, I would say any attacker or any other malicious program, it should not be able to read the content of that memory without your permission. So there should also be provision for security. Earlier, what used to be that, these security primitives were embedded at a system level, at a programming level, or at a software level. Nowadays, with this unique characteristics that these emerging non-volatile memories such as RAM have to offer, you can also embed these security primitives within the memory arrays. So that is also what we'll discuss in this course. Then they should be highly reliable. You don't want your device to fail without any prior notice, or you want your device to perform without failure for the stipulated time over which it should work fine. Then temperature resiliency. This is another very important point. Why I'm talking about temperature resiliency is that the typical operating temperature in your CPUs is not exactly 300 Kelvin. It's not room temperature. Typical operating temperatures maybe 60 degrees, 80 degrees, depending on the application. And if you talk about automobiles, the memories which are used in automobiles, then in automobiles, these can go even to 200 degrees Celsius. So your memories should not fail when you are increasing the temperature to 200 degrees Celsius. Also, it should not fail if you are going for extraterrestrial applications in space. The temperatures are in some minus 50 degrees Celsius and so on. So your memory should perform even well, even in those temperature conditions. Then again, when I talk about extraterrestrial, applications in space, you have a lot of cosmic rays, right? You have a lot of gamma rays, you have a lot of alpha particles, which may bombard on these memory elements. And whenever they impinge upon any semiconductor, it leads to creation of electron and hole pairs. And that electron and hole pairs, it can actually lead to several single event upsets. So this single event upset, it should be resilient to that. It should be resilient against any of the radiation. So it should be radiation hard. That is also one of the important parameters. Then whatever memory you are talking about, it should be CMOS compatible. Why? Because most of the industries, this silicon and this CMOS process, this has been there since 1980s. So people have actually improved their technology upon the previous technology, and now it's very mature. And no industry would like to change the entire thing that it has accumulated over this period of 30 years and go for a new material or a new technology. So if it is compatible, if somehow using the same process, using the same tools, you can process even the memory technology or even the memory that you're proposing, then the industries would definitely accept it, adopt it. And that is why CMOS compatibility is a major advantage. Then there's this EMI, EMC, electromagnetic interference, electromagnetic compatibility. So what this essentially means is you are living in an era where there are a lot of wireless communications going on, right? You have a lot of telephone, you have a lot of RF communication, microwave communication, mobile phone communication, signals which are being transmitted through the space, through your local environment. So because of those radiations, because of those electromagnetic radiations, your memory characteristics should not change. That is what it means. Then memory window. The difference between storage of logic state 1 and logic state 0, that should be very wide. Why I'm saying that should be wide? Because if it is not wide, you have to make complex peripheral circuitries with high sensitivity in order to measure that. And typically what we want is that your memory array should be denser and memory array should be covering your entire area of the chip. However, if the memory window is small, you'll have to make very complex sense amplifiers whose area and energy would be very large as compared to the memory array. So if in your memory chip your peripheral circuitry is dominating, then you won't like to have such kind of memories. That is why memory window should be large, so that even with very simple sensing circuitries, you are able to find out whether the data stored is logic 0 or logic 1. Till this point, we are only talking about binary memories, that each of the memory cell can only store level 0 or level 1. But nowadays, we have several of these memories which can store more than 1 bits of information. So this is known as multi-bit capability. For instance, let's talk about 3D NAND flash memory, which is the prominent storage medium nowadays. So in 3D NAND flash memory, each of the flash cell can store 4 bits of data now. How can it store 4 bits of data? For storing 1 bit of data, it has to have 2 threshold voltage states, one for logic level 0, one for logic level 1. For storing 4 bits, it needs to have 16 different threshold voltage values or 16 different states. It can show that. So if it can show you 16 different threshold voltages, then you can store 16 pieces of information, or in short, you can store 4 bits of information. So that is how these multi-bit capability is essential. It increases your density even further. Earlier, one cell could store 1 bit. Now one cell can store 4 bits. So effectively, in terms of memory capacity, you are gaining by a factor of 4. So multi-bit capability is also a very advantageous thing which these 2-terminal devices generally offer. Then variability. As I told, for RMs, this is a no point, or I would say this is a kind of something which impedes its development. So variations between individual devices should be as low as possible. What are the sources of variation? One is process variation. So when you are fabricating these devices, even 2 devices in the neighborhood of each other or even adjacent to each other, you cannot expect that the characteristics of both will be same. So because of that, there is this variation in the characteristics. So that is something which should be as small as possible. then there should be flexibility of interfacing. I mean, it should be such that it can be, your memory should be such that it can be interfaced with several of these systems, CPUs, GPUs, FPGAs, and so on. Interfacing should not be a problem. Then there should be a flexibility in topology as well. Also, choice of selector device matters. I mean, selector device, if you use two terminal devices with selector, density is smaller, but your leakage current is low. Programming capability is high. So it depends on that also. That is one of the memory characteristics as well. Also, addressability, whether you need bitwise addressability or blockwise addressability. So bitwise addressability, you need to tune individual bits one at a time. So programming anyway, you have to do bitwise, but erase is something where, you know, this bit addressability and block addressability matters. So in flash cells, for instance, the whole block is erased at once, whereas in SRAMs or DRAMs, erasing is actually bitwise. So that is also something that needs to be taken into account as one of the memory characteristics. Also, the operating voltage or current. So this power is actually the energy dissipated or the power consumed by this. But the operating voltage or current is also an important parameter. For instance, I told that large cell currents are required in PCM devices. So that is one of the major drawbacks. Operating voltage and current should be such that it can be, you know, satisfied by the present technology nodes. For instance, let's talk about 7 nanometer technology node. Supply voltage that it has got is 0.7 volts. Now the flash devices, they are having, or the programming voltages typically in flash devices that are present nowadays is 20 volts. So with 7 nanometer technology node, if you integrate a flash device, it won't be able to power it. So flash technology is an independent technology that. So we need devices which can work within the power constraints or within the voltage and energy constraints of the present technology nodes. Last but not the least is scalability. So density is something which tells you how many cells per unit area, but scalability is something which tells you potential to reduce that area further. So we need cells, we need memory cells which have the potential to reduce their area further or reduce their dimension further without compromising with their performance or while improving their performance. So these are few of the memory characteristics which are really important, and we should always look for whenever you are going to take a wise decision for choosing any memory device or designing any memory device.